Welcome everyone to this presentation on multimodal large language models and vision language models. My name is Models. Today we will explore the architecture, training paradigms, applications, and research frontiers of these models that are reshaping how machines perceive and reason about the world. We will cover everything from the fundamental building blocks like vision encoders and projectors, to advanced topics like cross-lingual retrieval and document intelligence. By the end of this talk, you should have a solid understanding of how these systems work, where they excel, and where the open challenges remain. Let us get started. So what exactly is a multimodal large language model? At its core, an MLLM takes a standard text-only large language model and extends it with perception modules for additional modalities, primarily vision, but also audio and video. The key insight here is that a pre-trained LLM already encodes rich world knowledge from massive text corpora. The challenge is figuring out how to inject non-textual information into that existing knowledge framework. This happens in 3 stages. First, perception. We use pre-trained encoders like vision transformers, clip, or whisper to convert raw signals, whether pixels or audio waveforms, into dense vector representations. Second, alignment. We use learned connectors such as linear projections, Q-former, or perceiver modules to map those modality-specific features into the LLM's token embedding space. Third, reasoning. The LLM backbone then performs cross-modal reasoning, follows instructions, and generates text auto-regressively over these aligned multimodal representations. This 3-stage pipeline is the foundation of virtually every modern MLLM. Now let us zoom in specifically on vision language models, or VLMs. A VLM is essentially an LLM plus a vision encoder, giving a language model the ability to see. What makes this fundamentally different from traditional computer vision? Traditional CV models are bound by fixed classes. If you train an image classifier to recognize 10 object categories, it can only recognize those 10 categories. If you want to add an 11th, you need to retrain or fine-tune the model. VLMs break this limitation entirely. Because the output interface is natural language, you can instruct a VLM to handle classification, detection, OCR, summarization, visual question answering, and countless other tasks, all through text prompts. This means VLMs are zero-shot capable and prompt-driven. You do not need task-specific training data. You simply describe what you want in natural language, and the model leverages its joint vision language understanding to respond. This flexibility is what makes VLMs so powerful, and why they are rapidly becoming the default approach for visual understanding tasks. Let us look at the general architecture of a multimodal LLM. The pipeline flows from left to right through 4 main components. First, the visual input, typically an image or a set of video frames. This goes into the visual encoder, which is usually a vision transformer or VIT. The encoder converts image patches into dense feature vectors. Next comes the projection or connector module. This is the critical bridge that aligns visual features with the LLM's embedding space. The design of this connector, whether it is a simple linear layer, an MLP, a Q-former, or a cross-attention mechanism, determines how much visual information is preserved versus compressed, and this has enormous implications for model performance. Finally, we have the LLM backbone, which could be Llama, Vicuna, QN, Phi, or any other large language model. This backbone processes the interleaved visual and text tokens and generates output text auto-regressively. On the text side, there is also a standard tokenizer that handles the text input. The key design decisions in any MLLM are really about these 3 components and how they interact. Now let us dive deeper into the vision transformer, or VIT, which is the backbone of modern VLMs. The process starts with an input image of height H, width W, and C color channels. This image is split into non-overlapping patches of size P by P. For a standard VITL/14 configuration, P equals 14 pixels. Each patch is linearly projected into a vector, creating a sequence of patch embeddings. The number of patches N equals H over P times W over P. Next, we add positional embeddings so the model knows where each patch came from in the original image. Standard VIT uses learned 1D positional embeddings, but for dynamic resolution handling, techniques like interpolation are used in models such as Navit and AnyRes. These patch tokens then go through the transformer encoder, which uses standard multi-head self-attention and feed-forward networks. For VIT-L, that is 24 layers, 10 24 dimensions, and 16 attention heads. One important note, self-attention has quadratic complexity with respect to the number of patches, which becomes a bottleneck for high-resolution images. For MLLMs, we typically use all the patch tokens rather than just the CLS token, because the patch tokens preserve spatial information. For a 336-pixel image, with patch size 14, that gives us 576 visual tokens that get fed into the connector. CLIP, which stands for Contrastive Language Image Pre-training, is arguably the most important component in modern VLMs. Developed by OpenAI, CLIP was trained on 400 million image-text pairs using contrastive learning. The idea is simple but powerful. The model learns to maximize the similarity between matching image-text pairs while minimizing similarity for mismatched pairs. This creates a shared embedding space where images and text live together. The result is zero-shot transfer. The model can perform tasks it was never explicitly trained on by matching images to textual descriptions. For VLMs, C-CLIP matters for several reasons. It serves as the vision encoder backbone in most modern architectures. It bridges pixels and language through that shared embedding space. It provides strong zero-shot visual recognition across unseen categories. And when paired with an LLM, it enables flexible classification, retrieval, OCR, and visual question answering. However, C-CLIP has known limitations that directly affect VLM performance. The input resolution is capped at 336 by 336 or 448 by 448, which means fine details from high-definition images are lost. The training data consists mostly of short English captions, which leads to weak spatial and positional understanding. And CLIP is fundamentally English-centric, so cross-lingual performance degrades significantly without multilingual training data. These limitations are important to keep in mind as we discuss more advanced architectures. The projector, or connector, is arguably the most underappreciated but critical component in the MLLM pipeline. Its job is to translate visual features from the vision encoder into a form the language model can process. Think of it as converting what the model sees into tokens the model can reason over. The design of the projector determines a fundamental trade-off between fidelity and efficiency. On the high-fidelity side, linear and MLP projectors pass all N visual tokens directly to the LLM. This preserves maximum spatial detail, which is crucial for tasks like document reading and fine-grained visual reasoning. But the downside is high computational cost, because the LLM has to process all those visual tokens. On the high-efficiency side, Q-former and perceiver architectures compress N tokens down to a much smaller number K, typically 32 to 64. This dramatically reduces inference cost, but you risk losing fine-grained spatial information and the ability to read small text. Choosing the right projector is not just an engineering decision. It determines what tasks your MLLM can actually do well. If you need to read dense documents or understand detailed charts, you probably need a high-fidelity projector. If you are building a chatbot that needs to understand general image content quickly, a compressed approach might be sufficient. Let us compare the four main projector architectures in detail. First, the linear projection used in the original LLAVA. It is the simplest approach, a single linear transformation that maps visual features to the LLM space. It keeps all 576 tokens for a 336 pixel input and has only about 4 million parameters. The advantage is speed and simplicity, but it lacks non-linear feature mapping. Second, the two-layer MLP used in LLAVA 1.5, QuenVL, and InternVL. It adds a GLU non-linearity between two linear layers, giving about 20 million parameters. This provides richer vision-to-language mapping, while remaining simple. But like the linear projector, it does not compress tokens, so LLM input cost remains high. Third, the Q-former used in BLIP2 and InstructBLIP. This uses cross-attention with learned queries to compress N visual tokens down to just 32 to 64 tokens. It is much more complex at about 188 million parameters and requires a three-stage pre-training process. The massive compression reduces LLM cost, but the complex training and potential loss of fine-grained spatial information are trade-offs. Fourth, the perceiver resampler used in Flamingo and IDEFICS. It uses a fixed set of latent queries and multiple cross-attention layers to produce a fixed number of output tokens regardless of input resolution. At about 60 million parameters, it is lighter than Q-former but heavier than linear approaches, and there is an information bottleneck risk. Each architecture represents a different point on the fidelity-efficiency spectrum, and the choice depends heavily on the target application. We are now going to transition to the training paradigm section. Training an MLLM is not a one-shot process. It involves multiple carefully designed stages, each building on the previous one. We will cover pre-training, alignment, instruction tuning, and preference optimization with RLHF and DPO. Understanding these training stages is essential, because the training recipe is often what distinguishes a good MLLM from a great one. The training of an MLLM follows a multi-stage pipeline, and each stage has a specific purpose. Stage 1 is visual encoder pre-training. Here we train the vision transformer on large-scale image text data, or self-supervised data. Contrastive learning, as in CLEP, aligns image and text embeddings using the info-NCE loss. Alternatively, self-supervised approaches like Dino or MAE learn visual features without requiring paired text data. Stage 2 is connector pre-training, or alignment. In this stage, we freeze both the visual encoder and the LLM, and train only the connector module. The objective is image captioning loss, where the model predicts caption tokens conditioned on the visual tokens. This teaches the connector how to translate visual features into the LLM's language. Stage 3 is end-to-end instruction tuning. Here we fine-tune the connector, and optionally the LLM and encoder as well, on instruction following data. This data consists of image, instruction, response triplets, covering diverse tasks like visual question answering, image description, visual reasoning, OCR, and chart understanding. Techniques like LoRa and QLORA are commonly used for parameter-efficient fine-tuning, making this stage computationally feasible even for very large models. The key insight is that each stage builds progressively. First learn to see, then learn to translate vision to language, then learn to follow instructions using both. Let us look at the specific pre-training strategies that MLLMs use to bridge vision and language. Contrastive learning, exemplified by clip and align, is about aligning matching image-text pairs while pushing apart mismatched ones in a shared embedding space. This is what enables zero-shot generalization. Masked language modeling extends the classic BERT-style approach to the multimodal setting. The model must predict masked text tokens, but now it can use visual cues from the paired image to fill in the gaps, forcing it to learn cross-modal associations. Masked image modeling flips this around. The model must reconstruct masked image regions, which encourages deeper understanding of visual structures and how they relate to textual descriptions. Image-text matching is a binary classification task where the model determines whether an image and text are a genuine match. This develops holistic cross-modal understanding. Finally, visual grounding requires the model to locate specific objects or regions in an image based on textual descriptions. This is crucial for fine-grained vision-language alignment and enables tasks like referring expression comprehension. Most modern MLLMs use a combination of these strategies during pre-training, with contrastive learning being the most common foundation. Evaluation is critical in MLLM research, and the landscape of benchmarks has evolved rapidly. MMBench tests 20 different visual abilities through multiple-choice questions. MMMU uses actual college-level exam questions spanning multiple disciplines, requiring both expert knowledge and visual understanding. POPE specifically probes for object hallucination, which is one of the biggest failure modes of MLLMs. MathVista focuses on mathematical visual reasoning, requiring complex multi-step reasoning over visual content. DOCVQA and ChartQA target document and chart understanding, using metrics like ANLS and relaxed accuracy that account for the challenges of dense text and complex layouts. SeedBench covers 12 different evaluation dimensions including spatial, temporal, and compositional understanding. And WildVision uses real user queries with ELO rating systems to capture actual user preferences. There are important challenges in MLLM evaluation worth noting. Traditional benchmarks like VQA-V2 are approaching ceiling performance, making them less useful for differentiating models. The community is increasingly using LLM as judge evaluation where GPT-4 rates model outputs, but this introduces its own biases. Open-ended evaluation and user preference studies like WildVision and Chatbot ArenaVision offer more realistic assessment but are harder to standardize. Cross-attention is one of the most important mechanisms for how MLLMs fuse information across modalities. Let me walk you through how it works. The attention formula is attention of Q, K, V equals softmax of Q times K transpose, divided by the square root of the key dimensionality, times V. In cross-attention, the queries Q come from the text modality. Think of them as asking, what am I looking for in the image? The keys K and values V come from the image modality. Think of them as saying, here is what is available at each spatial location. The attention weights compute the relevance of each image patch to each text token. Then a weighted combination of the image values produces text-grounded visual features. This mechanism has several key benefits. First, fine-grained alignment. It establishes precise word-to-image region correspondence. Second, contextual understanding. Each text token can attend to the most relevant image regions. Third, it handles variable input sizes, accommodating different resolutions and text lengths. Fourth, it provides interpretability, because you can visualize the attention weights to see exactly what image regions the model is looking at when generating each word. It is important to distinguish between self-attention and cross-attention in the MLLM context, as they serve fundamentally different purposes. Self-attention operates within a single modality. The queries, keys, and values all come from the same input. In text, it captures how words relate to each other. In vision, it captures how image patches relate to each other. This is used in standard transformer encoder and decoder layers. Cross-attention, on the other hand, operates between two modalities. Queries come from one modality, while keys and values come from the other. This is the mechanism that enables information flow between text and vision. It is used in models like Llama 3.2 Vision, Flamingo, and IDEFICS. Let me give concrete examples. For self-attention, consider the sentence, "The cat sat on the mat." Each word attends to every other word, building contextualized representations that capture grammatical and semantic relationships. For cross-attention, consider the question, "What color is the car?" Here, the word car generates a query that attends heavily to the image region containing the actual car, grounding the language in visual features. Both mechanisms are essential. Self-attention builds rich representations within each modality, while cross-attention bridges the gap between them. After supervised fine-tuning, MLLMs can still exhibit problematic behaviors. They may hallucinate and describe objects that are not actually in the image, produce verbose or unhelpful responses, or generate unsafe content. Supervised fine-tuning teaches the model the format of good responses, but it does not fully capture what humans actually prefer. This is where preference alignment comes in, and there are two main approaches. RLHF, or reinforcement learning from human feedback, works in 4 steps. First, collect human preference data, where annotators compare 2 model responses to the same image and prompt. Second, train a reward model to predict which response humans prefer. Third, optimize the MLLM using PPO, a reinforcement learning algorithm, to maximize the reward model's score. Fourth, add a KL divergence penalty to prevent the model from drifting too far from its supervised fine-tuning baseline. RLHF is powerful, but complex and computationally expensive. DPO, or direct preference optimization, is a simpler alternative. It uses the same preference data, but skips the reward model entirely. Instead, it directly optimizes the policy by computing the log probability ratio between chosen and rejected responses. It is a single-stage training process that is much more stable than the full RLHF pipeline. DPO has been increasingly adopted for multimodal alignment, as seen in models like LLaVAR-LHF and QuenVL-Chat, because it achieves competitive performance with much less engineering complexity. Zero-shot and few-shot learning are among the most powerful capabilities of MLLMs. In zero-shot learning, the model performs tasks it was never explicitly trained on by leveraging the text-image associations it learned during pre-training. CLIP is the classic example. You can classify images into categories the model has never seen by simply matching image embeddings to text embeddings of the category labels. Frozen model approaches keep the LLM weights fixed and train only the vision encoder to produce compatible embeddings for tasks like VQA and captioning. A key insight that is directly relevant to my research is that multilingual LLMs can pivot zero-shot multimodal learning across languages. Models pre-trained on English-only image-text data can sometimes generalize to other languages, even surpassing models trained on native language data. This is a fascinating finding with direct implications for cross-lingual visual document retrieval. Few-shot learning takes this further by allowing the model to adapt to new tasks by observing just a handful of image-text examples. This is especially valuable when labeled data is scarce or expensive. The challenges include the critical importance of example quality, the difficulty of generalizing from very limited examples, and struggles when the new task differs substantially from the pre-training distribution. Despite the impressive progress, VLMs face several significant challenges. First, resolution limits. CLIP encoders typically accept only 336 by 336 or 448 by 448 pixel inputs, which means significant detail is lost from high-definition images. Tiling strategies and higher resolution encoders are being developed to address this, but it remains an active challenge. Second, weak spatial understanding. Because CLIP training data consists mainly of short captions without fine-grained location information, the models struggle with precise spatial reasoning, counting, and understanding relative positions. Encoder ensembling and spatial-aware pre-training are promising research directions. Third, long video understanding. Current context length limitations severely restrict how many frames can be processed from a video. Models like LongVila and hierarchical transformers are pushing context boundaries from seconds to minutes, or even hours, but this remains computationally challenging. Fourth, domain-specific gaps. While general-purpose VLMs perform well on common tasks, niche applications like manufacturing defect detection, medical imaging, or satellite imagery analysis require domain-specific fine-tuning, parameter-efficient adaptation, or in-context learning approaches. The models lack the specialized knowledge needed for expert-level performance in these domains. Let me highlight 6 major open problems and research frontiers in MLLM research. Hallucination and faithfulness remains a critical issue. MLLMs describe objects that are not present in images, and the root causes are still poorly understood. We need formal verification methods to address this. Efficient multimodal inference is an industry priority. Deploying MLLMs on edge devices and mobile platforms is challenging because visual tokens dominate the computational cost. Research into token compression, early exit strategies, and speculative decoding is essential. Cross-lingual visual understanding is an emerging area and directly relevant to my PhD research. Most MLLMs are English-centric because CLIP was trained on English captions. Extending these capabilities to Arabic, Chinese, Japanese, Korean, and low-resource languages is a significant open challenge. Unified multimodal generation is frontier research. Current MLLMs mainly generate text, but models like GPT-4o and Gemini are pushing toward unified generation of images, text, and audio, which remains very challenging. Spatial and 3D reasoning requires new benchmarks. MLLMs still struggle with precise spatial relationships, counting and understanding 3D structure from 2D images. This may be a fundamental limitation of the patch-based approach. Finally, safety and adversarial robustness is a critical gap. Visual adversarial attacks can bypass text-based safety filters entirely, and multimodal safety is inherently harder than unimodal safety. Now let us talk about document intelligence with MLLMs, which is particularly close to my research focus. Documents are special because they combine multiple challenges simultaneously. They require high resolution since small fonts need at least 1,000 pixels, while standard models only process 336 pixels. They demand layout understanding because spatial relationships like rows, columns, and headers convey meaning. They need text reading capability through either OCR or text-aware visual features. They involve cross-modality reasoning, since tables need both structural and content understanding. And real documents are often multi-page with cross-references. The MLLM approaches to document understanding can be categorized into 4 types. OCR-free pixel-based methods like NuGet, Pix2Struct, and GOT-OCR 2.0 render documents as images and train the VIT to read text directly. High-resolution MLLMs like UReader, DOCL 1.5, and Intern VL2 combine OCR text tokens with visual features. Hybrid OCR plus vision approaches like MPLUGDOCL and TextMonkey leverage both explicit OCR and visual encoding. And document retrieval augmented approaches like KernelPally, VisRag, and DSE encode document pages as visual embeddings for retrieval, using Colbert-style late interaction over patch tokens. This last category is directly related to my PhD work on cross-lingual visual document retrieval. Both zero-shot and few-shot learning are fundamentally enabled by transfer learning, which is the real foundation here. The process starts with pre-training on diverse multimodal data. CLIP was trained on 400 million image-text pairs, and newer datasets like LAION5B are even larger. During pre-training, the model learns broad visual linguistic associations that span domains, styles, and languages. From this foundation, zero-shot transfer allows the model to directly apply its pre-trained knowledge to completely unseen tasks with no additional training. This works by matching inputs to patterns learned during pre-training. Few-shot adaptation then fine-tunes the model with a small number of domain-specific examples. Because the pre-trained representations provide such a strong foundation, the model can adapt rapidly with minimal data. It is worth highlighting the multi-instruct work from 2023, which showed that instruction tuning across diverse tasks and instructions leads to strong zero-shot performance with reduced sensitivity to prompt variations. This suggests that the way we frame instructions during training has a significant impact on the generalization ability of these models. This slide addresses the core question of my PhD research. Why does visual document retrieval fail across languages, and how can we fix it? There are 4 main failure modes. First, English-centric vision encoders. CLIP and SIG-LIP were trained predominantly on English captions. This means the visual features they produce are entangled with English linguistic biases. When you try to use these encoders for cross-lingual retrieval, performance degrades, because the visual representation itself carries language-specific artifacts. Second, script diversity challenges. Arabic, Chinese, Japanese, Korean, and Indic scripts have fundamentally different visual properties from Latin scripts. OCR quality varies dramatically across these scripts, and tokenization mismatches compound the problem, because different scripts have different character-to-token ratios. Third, benchmark gaps. Most multimodal benchmarks are English only. The cultural and linguistic diversity in evaluation datasets is severely lacking, especially for Arabic document understanding. We cannot properly measure progress without appropriate benchmarks. Fourth, alignment failure modes. The cross-modal alignment learned on English data simply does not transfer well to other languages. This problem is exacerbated in specialized domains like legal or medical documents, where domain-specific vocabulary creates additional gaps between languages. My PhD research addresses these problems through diagnostic probing to understand where failures occur, evidence-driven interventions to fix them, and Arabic benchmark evaluation to measure progress. Aligning MLLMs with human preferences is significantly harder than aligning text-only models, and there are 4 main reasons. First, hallucination is multi-source. In text-only models, hallucinations come from the language model. In MLLMs, they can originate from 3 sources: the language prior, where the LLM guesses based on text patterns rather than what it sees, the vision encoder misinterpreting visual features, or the alignment layer failing to properly ground text in the actual image. RLHF and DPO need to address all three sources simultaneously. Second, visual preference collection is expensive. Annotators must compare visual grounding, spatial accuracy, and text coherence all at once, which requires much more careful attention than comparing two text responses. The community is exploring automated preference signals using GPT-4v as a judge, but this introduces its own biases. Third, cross-modal safety presents unique challenges. Visual adversarial attacks like typography attacks and adversarial patches can bypass text-based safety alignment entirely. Images can encode harmful instructions that text filters never catch. This means multimodal safety alignment must jointly consider all modalities. Fourth, there is an alignment tax. Preference alignment can actually reduce the model's raw capabilities on benchmarks. Balancing helpfulness, harmlessness, and visual grounding accuracy requires very careful reward model design and hyperparameter tuning. Let me briefly survey some of the most prominent MLLMs in the field today. GPT-4v and GPT-4o from OpenAI represent the proprietary state-of-the-art. GPT-4v processes images alongside text, excelling at chart analysis, object identification, and diagram interpretation. GPT-4o takes this further with unified multimodal generation across text, images, and audio. Claude 3 and Claude Opus from Anthropic emphasize safety and ethical AI alongside strong visual understanding. They are particularly good at document analysis, code reasoning from screenshots, and creative visual tasks. Gemini from Google is natively multimodal, processing text, images, audio, and video within a single system. It scales from basic interactions to complex multimodal synthesis. On the open source side, LLAVA and InternVL have achieved remarkable performance. LLAVA pioneered the simple linear projection approach, making visual instruction tuning accessible. InternVL2 handles dynamic high-resolution inputs and delivers strong performance on document understanding benchmarks like DOCVQA. The open-source community continues to drive innovation, often matching or approaching proprietary model performance on specific benchmarks. Cross-modal retrieval is about finding information in one modality, using queries from another modality. Let me walk through the key paradigms. Image-text retrieval, powered by CLIP, maps images and text into the same latent space. This enables applications like visual product search and retrieving abstract visual concepts from text descriptions. Video-audio text retrieval, using models like Videolama, matches video content with textual or spoken queries across multimedia databases. Cross-lingual retrieval leverages multilingual transformers to enable retrieval across language barriers. You can use an English query to find French or Arabic media without requiring parallel translations. Document retrieval, using approaches like Kernel Pali and Visrag, encodes entire document pages as visual embeddings. The Colbert-style late interaction over patch tokens is particularly interesting because it enables layout-aware retrieval without requiring an explicit OCR pipeline. Generative retrieval takes a different approach, generating new content from queries rather than finding existing matches, similar to how DALL-E generates images from text. Medical cross-modal retrieval links symptoms and diagnoses with medical images like X-rays and MRIs, improving diagnostic accuracy in healthcare settings. Each of these paradigms addresses a different real-world need, and they all build on the fundamental cross-modal alignment capabilities we discussed earlier. Let me explain how multimodal embeddings and alignment work at a conceptual level. The process has 5 stages. Stage 1 is modality-specific encoding. Text is tokenized and embedded using models like BERT or GPT. Images are processed through CNNs or vision transformers. Each modality is handled by a specialized encoder, optimized for that type of data. Stage 2 is dimensionality alignment. The embeddings from different modalities typically have different dimensions. We project them into a common dimensional space using learnable linear transformations or neural network layers. Stage 3 is joint representation learning. Attention mechanisms and fusion layers learn complex interactions between the modalities. This is where the model starts to understand how visual and textual information relate to each other. Stage 4 is contrastive training. The model is trained to produce similar embeddings for matched image-text pairs and push apart unrelated pairs. Cross-attention enables fine-grained word-to-region alignment, going beyond global image-text matching. Stage 5 is task fine-tuning. The joint embeddings are adapted for specific downstream tasks like retrieval, visual question answering, or captioning, while retaining the cross-modal understanding learned in earlier stages. This 5-stage process is the common thread running through virtually all modern MLLMs, even though the specific implementations vary. Let me highlight 4 active research directions that are pushing the frontier of VLM capabilities. Vision encoder ensembling combines multiple vision encoders like CLIP, DINOV2, and SAM to get richer complementary image understanding. Each encoder has different strengths, and combining them addresses the limitations of any single encoder, particularly for spatial and fine-grained tasks. High-resolution tiling, through approaches like AnyRes, Navit, and dynamic tiling, breaks large images into subtiles that are processed independently. This is critical for documents, diagrams, and high-definition content, where the standard 336-pixel input is completely insufficient. We can now effectively process images at 1000 pixels and above. Extended context length is being pushed by models like Longvila and hierarchical transformers. They are expanding video understanding from seconds to minutes or even hours, with context lengths exceeding 100,000 tokens. This is essential for applications like surveillance, sports analysis, and long-form video content. Multi-image reasoning enables models to compare, contrast, and reason across multiple images simultaneously. This opens up applications like before and after analysis, multi-document comparison, and visual chain of thought reasoning, where the model can reference multiple visual inputs in its reasoning process. Each of these directions addresses a specific limitation of current VLMs and is seeing rapid progress. As we advance MLLM capabilities, we must also address the ethical considerations and responsible development practices. Bias and fairness is a major concern. MLLMs can perpetuate or amplify biases present in their training data across both text and visual domains. Imbalanced datasets lead to disproportionate misidentification of underrepresented groups. Active mitigations include adversarial debiasing and fairness-aware learning objectives. Privacy and data protection raise important questions. Large-scale web scrape training data inevitably contains private information and copyrighted content. Privacy-preserving techniques like differential privacy and federated learning are being adapted for multimodal settings, but this remains challenging at scale. Interpretability is critical for building trust. Understanding how these models make cross-modal decisions requires developing new tools. Attention visualization, saliency mapping, and neurosymbolic methods are all being explored, but we are still far from truly interpretable multimodal reasoning. Cultural sensitivity is often overlooked. Current benchmarks and models skew heavily toward Western and English content. Cultural nuances in gestures, idioms, and visual conventions vary significantly across cultures. We need diverse evaluation frameworks and inclusive dataset curation to ensure these models work equitably for everyone, not just English-speaking Western users.